So in this short video, I just want to talk to you a little bit about light, some of its properties, and how it relates to colour. So light is part of the electromagnetic spectrum, which on the one hand, on the left-hand side here, we can see gamma rays through X-rays, and on the right-hand side, radio waves. And the only thing that changes as we move along this spectrum is on the left-hand side we have shorter wavelengths, higher frequencies, and larger photon or packet sizes, and it's that latter property which makes the left-hand electromagnetic radiation generally more dangerous than the right-hand side. But in the middle, between about 360 and 700 nanometers, we have what is called light, and that's part of the electromagnetic spectrum that we can see. So you might reasonably ask the question, what is it about those wavelengths that makes them visible? Why are those wavelengths coloured, whereas radio waves and X-rays are not coloured? Well, the surprising thing perhaps is that there's nothing about those wavelengths that makes them coloured. I would argue they're coloured simply because we can see them. In other words, we don't see those wavelengths because they're coloured, but rather they look coloured because we see them. And that distinction is really quite important to understanding colour. We can imagine a thought experiment, which is, imagine if instead of being sensitive to, say, 360 to 780 nanometers, our sensitivity was shifted to higher wavelengths, into the infrared, which is currently invisible to us. Now the question is, what colours would we see? People often ask me, what colours are outside the visible spectrum if only we could see them? And the answer is, there are no colours there. And my hypothesis would be that if we were sensitive to that longer range of wavelengths, say 700 nanometers to 1000 nanometers, we'd probably see the same colours, that is the red, orange, yellow through to blue colours that we see in the visible spectrum. And the current range of visible light, which we see now, would be invisible and would have no colours. So at the end of the day, what this means is that the colours are not properties of the light, they're properties of our perception. Colours are things that we see, that we perceive or experience. Although the spectrum is continuous, we tend to see bands of colours, and those bands tend to be red, orange, yellow, green, cyan, blue and violet. Newton gave a slightly different set of 7 colours. Some people claim there are only 6 colours in the spectrum. Now, when we think about light sources, we can characterise those sources by looking at how much radiation that there is at each of these wavelengths in the visible spectrum. And you can see there the spectral power distribution of the sun, which is approximately broad band right across the spectrum. On the other hand, a candle flame and a tungsten lamp both have much more long wavelength light in their distributions than short wavelength light. So this spectral power distribution is, if you like, a fingerprint or a specification for a light source. Now things look coloured because they reflect some of that light from a light source to us. So if you take, for example, a white t-shirt, it tends to reflect back all the wavelengths that fall upon it, and the visual perception of that will tend to be white or whitish. If you actually measured the reflectance spectrum of a white t-shirt, you'd probably get something like this. So the reflectance spectrum is the proportion or percent of the light that is reflected by the sample. So this sample, for example, reflects about 90% of all the light that falls upon it at each wavelength, apart from in this blue region where the reflectance is much lower, because normally white textiles or white paper, for example, often look slightly yellowish, and the reason for that is they normally have some impurities that are absorbing in that blue region. These impurities are generated particularly when these materials age or are exposed to heat or light, for example. Now, when we add a yellow dye to a t-shirt, the dye absorbs some of the wavelengths, allowing the rest of the ones that it's not absorbing, to be reflected as they were reflected before. Now, it's commonly believed that the t-shirt absorbs all the wavelengths apart from the yellow ones and reflects the yellow wavelengths. But this simply isn't true. That is a sort of simplistic way of looking at things. If light really was coloured rather than just looking coloured, it might be a very simple story. Things are yellow because they reflect the yellow wavelengths. Things look blue because they reflect the blue wavelengths. It's just not like that. If we think about the dyes that give rise to a t-shirt like this, they tend to absorb light, and those absorptions tend to be approximately normal or Gaussian shaped. So in this case, you can see that the dye has a maximum absorption at about 400 nanometers, and it's fairly broad band, falling off at longer and shorter wavelengths. What that means is that the light which is reflected by this yellow dyed object looks rather like this. So you can see that in fact this object reflects actually all of the visible wavelengths to some extent, because it's not zero at any wavelength, and it absorbs all of the wavelengths to some extent because it's not 100 at any wavelength. But you can see that it mainly absorbs in the blue region, which means in these middle and longer wavelengths light is reflected. So not only are the yellow wavelengths around about 560 in this diagram, not only are the yellow wavelengths not the only ones which are reflected by this t-shirt, they're not even the ones which are most reflected. This t-shirt reflects the red and orange wavelengths more than the yellow ones, which should make you start being curious about whether you understand why that t-shirt looks yellow in the first place. Well, we'll be coming on to that later. It's to do with the human eye and our perception, of course. It's the same process that underpins something called additive colour mixing. So if, for example, we take three lights, a red light, a green light and a blue light, and these lights, imagine if it's single wavelengths, single wavelength red, single wavelength green, single wavelength blue, and we shine these three lights onto a white projection screen where they reflect off, and then we overlap the three lights. So where the red and green overlap, we get yellow. Where the green and blue overlap, we get cyan. Magenta, where the red and blue overlap. Where all three overlap, we get white. Now imagine if we then measured with a machine, we can do that with a spectroradiometer, the light which is being reflected by this projection screen. All we find, we get single wavelength green here, single wavelength red here, single wavelength blue there. What would we get if we measure in this yellow region? So I think lots of people intuitively think that somehow the red and green wavelengths magically combine to make the yellow wavelengths. But if we measured what's happening there, we get this. In other words, we still have the red and green wavelengths, but those two wavelengths together look yellow. So in fact, have these lights mixed at all? The word mixing is really a little bit misleading. The red and green lights are simply coincident in the same place. And our visual system is very, very poor at even telling whether a light contains one wavelength, two wavelengths, three wavelengths, or many wavelengths. Two samples can be physically very different, but nevertheless appear to be identical. So in this case, if you have single wavelength yellow light, you have that stimulus shown on the bottom. If you have a mixture of red and green wavelengths, you have the same colour exactly. We're incapable of spectrally analysing any colour or signal, any light signal. So what this means is simply measuring the amount of light reflected by a sample at each wavelength, which is physics, is actually insufficient to measure colour. There's something else going on that we need to take into account, and that thing is the human visual system.